Okay, now I think the DE folks can hear me too. Uh, what I'm saying about the lab reports also goes the uh, for the reports that are in this class. Most of the class or most of the reports in here, um, like down here for these projects, don't require the formal report. Short report's fine, but you still need to read some of this information. Uh, what I wrote on several labs uh, for the DE folks, you need to know I just finished grading a bunch of labs for the first time this semester. I've been way behind on my grading. Um, I'm going to catch up soon, though. I tell you what, uh, each one of those reports took me from anywhere from 30 to 45 minutes to grade, somewhere a little longer. And I was so tired. It took a couple of days for me to do it. And I hope that most of you, if you knew that you had some friends getting them and then you weren't, you were looking like, where's mine, where's mine, where's mine? Uh, I stopped because I was getting so tired that I knew your grade would really suck if I kept grading them. Right here under this digital systems lab, there are several things here that are I think you should read before you turn in any report. And I forgot to say that to this whole class. But the report guidelines and the tips, and those especially. Then in our lab, we also have the required sections for the reports, and I can put that on the other class too. That's no big deal. But it looked to me like nobody read those, and that's fairly important. Uh, I mean, this one right here, it basically use formal tone, no personal pronouns, none. Uh, you got to use a passive voice. So instead of saying something like, I measured this or that in the lab, you have to say this or that was measured in the lab. Okay? So it has to be passive, no personal pronouns. Can't use things like can't, right? Don't use words like don't. Um, this is the most serious one. This is the one that can get your name put over in the Dean of Students office and on file there for, I think, 5 or 6 years until they decide, okay, you probably aren't going to do this again. You have to reference things. If you go to a website and you look at something and then write something down, it doesn't even have to be the exact same words. Just if you've looked at it and then you write something down, reference it. And this rule of thumb, if you're not sure, should I reference or not? Reference, do it. It's not going to hurt to reference it. Okay. Um, Now there were some that I couldn't help it. Just didn't exactly sound like something you guys would have said. So I looked. Or there was several that you guys looked on Wikipedia. I'm going to have to say no to Wikipedia from now on. Okay? Because there were some that you guys used, and it sounded to me like it was wrong. Just dead wrong. So somebody's put information out there, they haven't had time to check it yet, and it's wrong. And then you guys come along and see it, and you go, whoa, that sounds good, and you put it in your report, and I'm going, slash, that's wrong. Okay, but it sounded so wrong that I went to Wikipedia to find out, did you get it right, or did you write it down wrong? And then I found what you had was almost word for word what they had. So then I go back and look at the report, and there's no quotes around there. That there is usually you've got a folder on the way to the Dean of Students office saying you have committed plagiarism. Okay. If you write something down, if you find yourself saying, or doing one of these things where you highlight this whole line and you're going to copy and then paste it, you got to put quotes around it and tell me that you got it from some other page. Some of you don't know you did this, so I've got to point it out. That's why I've said come to my office about it. If any of you want to come talk to me about it, that's fine. I know I won't be here much more today. I can stay for a little while and talk if you want me to. Tomorrow I'll be on campus, but I'm in a meeting I would rather not be in, but I'm going to be in that meeting from 11 to 3. Wonderful. So you might be able to catch me from 10 to 11, and you might be able to catch me from 3 to maybe 3:05, because I'm going to be wanting to get the hell out of here after that meeting. I know a lot of you didn't read this because it says in here very clearly, tables should be identified at the top. Everything else should be identified at the bottom. And I don't know how many times I was cutting the table from the bottom and putting it at the top and then highlighting it, telling you, don't, this is where it belongs up here. And I showed this to you the first day of class. Okay, so I know I did, and I know it's like you are right now. You're bored stiff. You're wishing, it's like, I wish you would go on to something else. I don't want to listen to this bullshit, and you don't want to do it. And then you're going to have a lab over in the dean's office, and the dean of students. That's more important because that's the dean for all the university, not just the dean for the College of Education or Engineering. So it's real important to listen to this and not get in trouble on this. I know it's boring, but you've got to do this right. Here, write a concise summary of the entire experiment. Purpose of experiment, relevant theory, requirements, constraints, all that stuff. But there's other stuff in here that if you read it, it's pretty clear. You don't go step 1 or bulleted items all the way through saying, basically step 1, do this, step 2, do. I already wrote the lab. I know what you had to do. I don't want you to tell me what you did. Go hit File, New, Open, or whatever, choose a directory. I told you to do it. I know what I told you to do. Don't tell me that back. And there was a couple that were like that, and it's like, that's an automatic rewrite. Put a lot of work into it, but it's an automatic rewrite. So you have to read this stuff, okay? The abstract, it tells you on here that the abstract, where is it? Somewhere in here it tells you that the abstract is single-spaced on the first page right after the table of contents on a page by itself. Oh. And the, okay. Usually about, that's not, That's a rule of thumb. And what I do now, I don't understand even, I know who wrote this, but I don't understand what they mean by that. It's a hook that makes those that matter want to read it. Uh, what I've done on every paper that I have published, and I've published enough. I should publish more, but I publish enough. Uh, I went through the report after it was the last thing I wrote. So if you're missing anything in your report, it should be the abstract because you forgot to put it in there. Everything else should be there. But the abstract you write last, you go in and pull, and this is how I do it anyway. I pull an important sentence out of each section of the report. Okay? Something out of the introduction, something out of the purpose maybe. And the purpose, I pretty much let you make that up on yourself. And I'm going to get to one of your questions in a minute. The procedure, the results, and a conclusion, all that should be stated somewhere in the abstract, and it is not going to flow. So you take those sentences from at least those sections, and then you massage it a little bit and make it work together. Okay? That's how you write that abstract. In papers I've read, I can read the abstract and I've got a damn good idea what is in that whole paper. And so I can then go directly to the results to see, is this what I want? And then after I read the results, if I'm not sure how they got them, I want to read how they got them. So I don't read reports from from the first page to the end. I'm bouncing around. Abstract is first. Procedure should be very concise, but is narrative form. See, here it is. The abstract. I know I must have put this in there. The abstract is the first item in a report, but the last to be written. To write the abstract, copy a sentence from each main section of the report, blah, 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 and then make it all work out. Okay. Anyway, this stuff is out there. The lab report guidelines, the required sections, and for those that are doing reports for this class, you need to know format and short reports. And you need to probably read through this one too, just to make sure you're doing it right. Because every report you do for UNCC, you have to do it this way. Okay? So you may as well get used to it now.
I started putting those title page on our projects too. Is that fine too, or?
What, my title page?
Mm-hmm.
The reason I put my title page out there.
No, I mean like on the projects, like the projects.
Yeah, you can use them for the projects too. But you made me think of something that I put out there. So here I've got it. You look at it and you're thinking, okay, this is stupid. I can make up my own. And then I've got this page and you're going, what is this for? And then I've got this page and you're going, what the hell is this for? What I've done is I've set Word up so that it's in the different sections, okay, so that you've got this report titled, this is page I, but it doesn't show it up here. I already fixed it, so it doesn't do it. And then you can fix all this stuff, and then you come down, this is, I'm sorry, that really should have been I, and this should be II. But anyhow, then you've got this section, and that's labeled I, not not 1 or 2 or something like that. But notice this one doesn't have that border around it either. So I've set this up so you can copy this and start your report this way, and this part's done for you. And then 2. And I've got the numbering in the right places, and I've got it all set up right. So, and after this, if you do an appendix, you do have to change that. But by then, you can go back and see, how did I do this, or come ask me, and you can figure that out. But that's why I put that out there. Now, this is the older version of Word, so if I need to update that to a newer version, just let me know, and I'll do it. Okay? All right. Now, so, and then if I read through that whole report or graded report, because I spent time writing stuff in there, you'll see where I changed stuff. So go ahead and read it. I didn't write it for me. I wrote it for you. So, and here's where you can get to my website. But I wrote it for you so that you could benefit from that, not get in any trouble. And there are faculty that believe, including me usually, but that you already know what's cheating and what's not cheating. And so you don't get one chance. I go ahead and do it the first time. Okay? This time, the way it was, I thought, no, this is something that some people don't understand, so let me talk to them about it. And then the word can get spread around. And if you want to call me an asshole, do. What I'm trying to do is keep you from getting in trouble in this class, any other class, especially the ones that are not in the College of Engineering, where they, students go, I don't want to take this class, it shouldn't be necessary, blah, blah, blah. And the teachers overhear that and they get pissed off. And then they say, I'll show you how important this class is. And they start throwing people's papers into the dean of students. And all of a sudden you realize their course is important too. Is there something crawling on you?
Yeah, spider.
Get it off him. Nobody wants a spider on him. There it is on the wall. Here, you want to get him? Did you get him? See, I use this stick for everything. It's like, whap. Okay. I want to show you the next the next project you have to do. You were all asking, or not all, but a lot of you were asking me, please, please, please extend the date. I said no, because I had said no already. This is the next one. This one's going to take a little while. I gave you what? It's due November 9th. So I only gave you, I've already extended. No, I didn't extend this. This one's only 2 weeks away. And we have to learn how to do this. And then the very last one, look, and you have to do these. I mean, if you don't, you get a 0, and that's going to really kill your grade. But you're either going to do this one, or you're going to do the traffic. And there was another one I was going to put in there about a elevator, but I haven't got it all cleaned up yet. So anyway, this is the one that most people choose, because actually it's the one that's the most clearly defined. This thing here, I've got that you've got till December 3rd to turn it in. This one is a doozy. Okay, this one is a doozy. When people turn it in, their state diagram is so large that it takes 5 or 6 sheets of paper to have their whole state diagram. Okay, typically they have 35 states. Okay, 26 is where they go state A, B, C, all the way to Z. Well, they usually get up to HH or II, something like that. So, it's 30 something states in this thing, and it's going to take a little while. You don't start this the day before. Okay, you do not. And I had so many people asking for me to extend it, I could tell you just got started and didn't realize it was this much. So in my other class, and I'm going to do it in here day of and day before a report is due, I will not answer emails on it or questions. I won't. You have had to have started long before then to get me to answer some questions on it. Okay? And a lot of you do. But some of you that are waiting to the last minute, I'm not going to I was getting into a panic Sunday because I'm grading stuff and I'm getting all these emails coming in going, can you answer this? Can you do this? Can you help me here? This isn't working right. And I'm like, oh no, what do I do? I got to help them. I got to really read this. And I'm thinking, what the hell am I getting in a panic for? So it was like, that's it. My wife says, didn't you used to not help them? I said, yeah. She's all for me now. Let's put it that way. She's all for me. So, uh, you know, don't ever go to her to try to get me to lighten up because she's going to come at you like a banshee and try to tell you how you need to be working harder. She's worse than I am. Okay, let's get started on these state machines. Okay, and look at the projects for the rest of this semester, or what I have to go through. Finite state machines. Example: these two here are, and the alternate. These three basically are going to get you more ready to do this one. Okay. Then I've got the pump. Well, if you look at the lab, and you guys in the DE class will be taking lab this summer, and I've asked to teach it mainly because I make more money, not because I want to hang around with y'all. Well, that was real nice, wasn't it? I thought I'd be honest about it. Okay, my daughter and her husband are very happy. They are now officially homeowners. They signed the papers. Uh, so they're feeling good about it. Anyway, okay, in the lab, there's this one down here at the bottom that says extra credit submission. And if you look at lab 8, I've got it turned off right now. It's this pump. What do? I go ahead and show you in here the pump with JK problem, flip-flop. So I go ahead and kind of show you how to do it. This one is a little different so that you're not doing the exact same thing, but that was to do extra credit for the lab. And after the grading I did on this first one, some of you are going to need extra credit. Okay, so then I go into vending machines, and this one here is so similar to this last project, except instead of doing the candy machine, this vending machine, it just does drinks. It does water for 75 cents, cola for 50, and beer for 50. I know everybody would love this, but if that beer is 50 cents, I don't think I'd drink it. I like good beer. I don't like 50-cent beer, okay? But I go in and I show you all the, look at this, how crazy it can get in no time flat. This is just those three things and putting in some coins and uh, you know, you've got to develop the tables and the state tables and the all this stuff, and then you finally develop the VHDL. Okay, you develop that to match this table, and then you got to come in and you got to test it, and you got to prove to me that your VHDL worked right. And you're going, oh shit. Yeah, I would too. Here's my traffic controller. This is the way I did it. But what happens is most people go, I've got an example here. So they try to do the traffic controller this way. And honestly, I put it out there because I thought this is the way I would approach it. So, what the hell is this one about? Well, I didn't define what RS and T are. All I did was show that they are. These are inputs to the machine. Now here, if you're in state A and the input S or input T are 1, you go back to state A on the next clock cycle. If S is 1 and T is 0, so here they're both 1. Here S is 1 and T is 0, you go to state B. If R is 0, you stay in state B. If R is 1, you go to state C. If R is 0 and T is 0, or if R is 1 and T is 1, then you go over to state B again. This is starting to get complicated. This is a simple one. And then if R is equal to 1, you go to state C. Now I've got this one. If R equals 1 and T equals 0, you go to A. This one messes people up. If S is equal to 0, you go from state A to state C. Okay, you go, if R equals 0 and T equals 1, then you go from C to D. What I'm saying about this one, S equals 0, is associated with this transitional line going from A to C. This transitional line is unconditional. When you get to state D, you automatically go to state A the next time. Doesn't matter what any of the inputs are. Okay? So here I say the output of the system are the outputs of the flip-flops. Well, we're going to be talking about that in just a minute. I told you in here the other day that that this was the flip-flops, and then you come here to the output circuit. Well, the flip-flops can have different state numbers, 0. Let's say you have 3 flip-flops, so if they're all 0, you got state 0. If you got the one that you've decided was the least significant bit, so you got 0, 0, 1, now you got a 1. And if you got 0, 1, 0, now it's a 2. Okay, so those outputs from those flip-flops are the outputs to the machine. Okay, and they are telling you, what it's telling you here is that you are in state A, state B, state C, or state D. I've also said you have to do this in a special way. It's called one-hot encoding. And I'm going to show you an example of what it means to have one-hot encoding. So you got to show me that you're, oh, there's where it says it. You got to use negative edge triggered D flip-flops. You must include all your Carnot maps and state equations in here. You got to develop and test the circuit, so you got to do it in Xilinx. I think I've got in here, okay, that you have to do it by schematic capture. Okay, Then you have to do another one where you do the VHDL code. So you got to do it both ways. Do it with the schematic and do it with VHDL. So this one is not one that you sit down Sunday afternoon after dinner and say, that was a good dinner. Now I think I'll get started on that homework that's due tonight. I am not going to get in a panic for you. I'm not going to do it. I'm going to snicker at you. And I'll eat a Snicker at the same time. Okay, so there's a lot to this one. Please do me a favor and read this one tonight and get an idea what it is. And I'll bet if you've already turned in this one, you'll start working on this one. Please do. I want you to get good grades. Then your final exam is like 2 or 3. I mean, there might be 10 problems, but it's like breaking this one into 6 different questions and breaking this thing into 4. And it's not exactly the same thing. I'm saying one of this difficulty. So you're going to be seeing something similar again on the final exam. So please do that very carefully. Now, finite state machines. Now, I'm going to go through it. You can all now see my videos, even the folks in here. And these are the things we're going to talk about. The difference between Mealy and Moore. I don't care which way you do it, a Mealy or Moore machine. That's up to you. But there are some people that, especially a lot of you, will go to grad school and your faculty will say it's got to be a Mealy machine or it's got to be a Moore. And the one is harder than the other. These are synchronous. You can either have a synchronous circuit where it uses a clock or an asynchronous where it's not using a clock. This one is if it just changes and it's the state of the machine that makes it change states in the state machine design. This one, it's the state of the flip-flops or the state of the machine plus the synchronous of the clock. So we're going to be doing all synchronous machines. The reason I don't like this one is if it's asynchronous, let's say you've got, you've labeled your, sorry, my legs are killing me today. Say that you labeled your state A as 0, 0, 0, B as 1, 0, 0, 1, and C as 2, so 0, 1, 0 on the flip-flops, and you go to state A, and then state B, and then state C. Well, if flip-flop 1 changes quicker, you went back to state A first, and then you went to state C. Do you see what I'm saying? It might go, when you're in state B, I'm sorry, where the flip-flops are 0, 0, 1, and now you're going to state C where it's 0, 1, 0. If the first one changes quicker, it would be 0, 0, 0 momentarily and flip over to state A and then flip back to state C. You don't want that to happen, so synchronous state machines work off that clock, and you have a little bit more control by doing that. Okay. Here, this blue line says that that part of these inputs, now this says W as an input, there can be 50 inputs here. Doesn't matter. You know, it can be as many as you want. It can be a whole bunch of flip-flop or a whole bunch of inputs. But what's important about this is, let's see, let me go back. That this input could go also to the output. So it could be used to control the state of the machine and control the outputs. So it could, I mean, that can get a little complicated here. And then it can also, the current state of the machine, this is what makes it a state machine. The current state, which is all these flip-flops in here, and I don't care if there's 2 or if there's 102, their value is fed back to the beginning, and that's what makes it a state machine. Okay? Because you go like, when you go to a stoplight, they're state machines. Do you ever go up there? I know you've seen these before, but typically, do you see the lights go uh, green and then yellow and then red? Do you see that? Sure. Do you see it then go yellow, like get ready, and then green, go? No, we don't see that because we're ready all the time anyway, right? We'd have too many accidents if there was a yellow to get ready there or another color to get ready. So you don't have something like that. So if the lights are yellow, that's a certain state of the machine. The next state is the lights have to be red. Now, I don't know what's going to cause that state, if it's a timer or if it's a number of cars that are trying to get through. If it sees, oh, I got 5, let me let them through. I don't think it does that. But it seems to be on a timer, right? And then it goes over to the next one. But when it's yellow, it goes to red. It doesn't get to red any other way. Okay, so because the state is yellow, it goes to the state that's red. And that's kind of important. Primary inputs here are W, the register outputs are Q, but they're also the inputs to the input part of the circuit. Okay, and then we have our present state and our primary inputs that control the finite state machine is what they call it, because it has a finite number of states. Okay, the Moore machine acquires inputs from register outputs only. Okay, the present state of the machine, and this blue connection does not exist. Okay, so the let's see, more finite state machines acquire inputs from register outputs only. That sounds like this one. It should be saying that the outputs, I might have to go in and change that. The outputs are from the register outputs only. They don't come from these inputs. I do have to change that. So in other words, this connection in blue does not exist. A Mealy machine, the register outputs and primary inputs will allow you to change these outputs. I had a student here a while back, and I personally don't like Mealy machine or Moore machines. I like to let me let me reword that. I don't like the Mealy machines. Almost everything I do is a Moore type machine. So those are the examples you're going to see. This lady that was in my class loved the Mealy, and it was a problem for me to grade them because I had to really work at it to get them graded. But I knew one thing: she wasn't cheating. You know, nobody was copying her, and she wasn't copying anybody else. She was doing them all on her own. And if you'd have met her beforehand, you'd have said that she's probably not capable of this. And it just the way that she did this, it really turned me around in the way that I thought of her and the way that she did her work. Okay, here's the design steps. They're not always required, not every step, but a lot of times they are all required. So the first thing is you're going to have to obtain the specifications of the circuit. That means I'm the I'm the one that's hiring you to do this, so I'm the employer. I've got to describe to you how it works. Now, almost every time that you do anything like this for some employer, you have to go so far through this, and then you want to show them, like, this is what I think you're talking about. So in our situation, we might go all the way through the Xilinx stuff, maybe not come up with a circuit, right? Maybe just come up with a VHDL where we describe the circuit and show him the outputs on a simulator and say, is this what you meant? And he says, no, that's not what I meant at all. Then you figure it out and you go back and you work it out until he's going, yes, that's exactly what I meant. And because most employers are not the technical people that know how to put it to explain how they want these circuits to work, and we're not the kind of people typically that know how to get that information out of someone. Okay, so in other words, we can communicate pretty good with each other, but not with real people, right? I'm sorry, Chan Ho knows the difference between the people in the real world and those other people, right? And those other people, they don't know how to communicate with us. Does anybody watch that show, Scorpion?
OPXT.
Huh? The Scorpion show? I'm the only one that sees that. There's a bunch of,
Like the smart people that
yeah, they're really, really smart people that have the high IQs, and they got this one girl on there that is just normal. And she communicates the real world to the rest of them.
T1000 up too.
She what?
The guy, the older guy that plays like that, he was the T1000 back in the day. I'm sorry, that's the only thing I know him from.
Okay, but okay, it's based on a real guy, but he's also the one that's coming up with the show, so he might be. This might be a little self-serving here, you know. It might be. Okay, so we obtain the specifications of the desired circuit. Okay, so in here, in this first example I'm giving you, this is the easiest kind of example I can give you because it has no inputs. It just goes through a sequence of stuff. Okay, so here's the whole example. It is going to continuously perform the count 0, 4, 2, 1, 0, 4, 2, 1, 0, 4, 2, 1, and that's all it's ever going to do. So there's the specs. Okay, then we're going to derive from that the state of the machine and develop a state diagram from that. And the state diagram should show all the possible states, and I usually do those with a circle. I normally do those with a letter, but we're going to be changing those over to probably to bits, and so I'm gonna call them A, B, and C and stuff like that. And I probably shouldn't, because normally we call the bits lowercase c and then lowercase b and a, and so sometimes it can get a little confusing, but I'll try to keep that from happening. And then provide the conditions for which you move from one state to the next. So let's see how that goes. Here's my example of that design. We start at 0. There's no input that tells us to go to 4. We just go to 4. There's no input that tells us to go to 2. We just go to 2. So this is all based, since everything we're doing is synchronous, this is all based on a clock. So every clock cycle, we go from 0 to 4, the next clock cycle 4 to 2, next clock cycle 2 to 1, next clock cycle 1 to 0, next one 0 to 4, okay? And I just did this as an arbitrary choice to start, okay? So that is my diagram of saying this, I think, shows what that state machine is supposed to be doing. Okay, it does have all the possible states, and it does show the conditions for progressing to the next state. It doesn't, there is no conditions. Now, I could have something like, there's an X variable and a Y variable, so X and Y have to be 0 to go to this, and X has to be 0 and Y a 1 to go from 4 to 2. I could have something like that, but I don't. And these numbers are the output of the machine. Okay, so we've done this. We've shown it. We've shown the conditions for moving, and then from that we have to develop a state table from that state diagram. So here's a state table. It's about as simple as it can be. Now, it's going to expand. So what I normally do is put this state table, the original version, in a spreadsheet. And most people do this, and I think it makes it a little bit easier. You don't have to. You don't have to. That's up to you. If you're just drawing it out on paper, that's fine too. But here it shows that if our current state is 0, is our next state ever going to be 2? No, the next state's always 4. If our current state is 4, the next state is 2. If our current state is 2, the next state is 1. And it shows that on there, right? It's very clear. If our current state is 2, our next state is 1. Okay? Now, we're going to use some flip-flops here. Decide on the number of state variables needed to represent this, and then minimize that if possible. Now, what I mean by that is how many state variables is like how many flip-flops am I going to need? I've got numbers from 0, 1, 2, and 4. That does not mean that the numbers have to be 0, 1, 2, and 4. The numbers could be 0, 1, 2, 3. Right? So I could have, 2 flip-flops. Takes 2 flip-flops to come up with 4 different states. So we could do it with 3 flip-flops. We could do it with 4. And say it's one hot encoding where only 1 flip-flop is high at a time, and that would be 1 hot encoding. So when the one that we call flip-flop 0 is high, then we're in state 0. When we got flip-flop 4 high and all the other 0, we're in state 4. Okay, or we can do it the way this says, decide on the number of state variables and then minimize it if possible. So it depends on what you're doing. I say let's try to minimize this if possible. So we're going to use 2 flip-flops, I believe is the way I've got this going. Then choose, so with this I've got, well, we've only got the 4 possible states, but I went ahead and said, let's use 3 bits. Okay, so I did do it a little bit different than I want now. And the reason was I wanted to say 0, 4, 2, and 1. I could have done this where State 4 was actually a 3. So we had 0, 0, 0, 1, 1, 0, and 1, 1. But then the output converted this to 4. It was 3, but it converts it to 4 if we want it. But I decided to do it this way. That's right. Because I want it to be the easiest one we've seen. Okay. So we are going to have 3 flip-flops. We're going to have 3 state variables. And I'm calling them QA, QB, and QC. The outputs of the flip-flop. Now here I've got lowercase QA, QB, and QC. And I'm saying that that's what the next state output is going to have to be on these flip-flops. So if this is the current output, this is the next output. So how do you want me to do that? Say that this is T and this is T plus 1? I mean, there's different ways of writing it out, and different books do things different ways. I do current state, next state. I've got capital Q's here and lowercase q's here. Okay, so I do know that QA, to go from state 0 to the next state, which is 4, QA has to change from a 0 to a 1. Oops. QB stays a 0, QC stays a 0. And then the current state, I'm in state 4. Now we could have a problem here, right? Because we've got QA having to go from 1 to 0, and at the same time QB going from 0 to 1. Now if those don't happen at exactly the right times, we're going to have a glitch. Just remember, there's a possibility of a glitch here. Okay, here we're in state 2. This is the binary number 2, and here again we've got a possibility for a glitch. We could, because even though QA stays a 0, QB goes from 1 to 0, and QC goes from 0 to 1. Okay, and this one, no possibility of a glitch. We just go from 1 to 0. Everything okay? Nothing? Am I going too slow for you? I'm going too fast? Really? Pierre, you're just messing with me. He almost stole my stick a while ago. So if you guys see me standing somewhere and I'm stickless, then look for Pierre. He's around here somewhere with my stick. And I want you to go find him, hit him with it, and then bring me my stick. Okay? And then I'll find him and I'll hit him with it too. Okay. Choose the type of flip-flops that'll be used. Now, it depends. Now, if we're going to do VHDL, we don't care about that. We let Xilinx, or if we're using Verilog or some other kind of system, because there are other systems like Quartus, if you use one of those, it might decide. Let it decide. It's just let it decide. But here, we're going to choose which flip-flops we're going to use, because the first thing we're going to do, or the first circuit we're going to create, is going to be a circuit anyway, not VHDL. So here I chose D because they're easy, right? So I know that I'm going from 0 to 1. So what do I have to have on DA for it to change from 0 to 1? I have to have a 1. Now, if this was a JK, I could have where both J and K were high, or I could have J high and K low. So I've got one of those situations where J matters. It has to be a 1. K doesn't matter. So I've got, if this was JK, I would have 1 for J and I don't care for K. All right, does that make sense? Okay. Then to go from 0 and stay 0, D has to be a 0. So we're defining what are our inputs going to have to be for each transition of the clock to make sure that we get to the next output. So here's our current state, our current outputs. We want to change them to this at a transition of the clock. Okay, so in doing that, here's the D flip-flop table, and we're showing how to do that here. So then putting in all the values, I just said that and for a D, it's usually this way. Now, it's different if you have a set of inputs also, okay? But if it's just like we have it where there's no inputs that are telling us how to go from 0 to 4, then we've got something like this where D is just whatever the next state Q's are. And that makes it pretty simple. Okay? So now we have to develop the input logic or the next state logic or the input logic circuit. So here we go. But before we can do all this, we got to include all the possible states. Now we don't have to, but I think we should, at least until we get used to things, so that we see everything. So here shows all possible states for 0 or for 3 flip-flops. So we go from 0 to 7. Now notice here, if we got 3, we're not doing anything here. You may want to do something like always go back to 0. Okay, you may want to do that. So for all these states that we never use, you might want to always say go back to 0. But the thing is, it should never get in one of these other states, right? But what if you're in a circuit, you're running your circuit outside, and it's susceptible, possible to a little bit of static, and it could make it go to state 5 there. You don't tell it where to go. It could get stuck. So you might want to say make it go to all zeros. It doesn't, that's up to you. But I've got don't cares here. I don't care what it goes to. It can get lost and just flounder around for all I care is what I've got here. Okay, so now I have to figure out what the inputs to the registers for each different state. So we've got to develop that input circuit. We've got to use Carnot maps to do it. We've got to develop the state equations, in other words. Now this is where everything that we've done so far in this class is coming together. When we had the Carnot maps, we had, for a 3-bit Carnot map, we had cells that were numbered 0, 1, 2, 3, 4, 5, 6, 7, right? Here's cell number 0, 1, 2, 3, 4, 5, 6, 7. Here's A and B. Here's C. We got them, okay? So we've been working on rows. Now we're working on a column because we're saying, I want to know what this flip-flop, its inputs A, B, and C need to be. So for DA, I have to have a 1 in cell 0 and a 0 in cell 1. And then I got to have a 0 in 2 and a don't care in 3. I got to have a 0 in 4 and a don't care in 5. And then a don't care in 6 and a don't care in 7. So writing that equation, the input to DA has got to be not QA and not QB and not QC. I've got the state equation. the second one is going to be these. These are going into 0 and 1. These are going into 1 or 2 and 3, and so on. So let's do it. We got these two go into 0 and 1. These two go into 2 and 3. So 0 goes into 2 and don't care goes into 3. Then we go to 4 and 5. We got 1 and a don't care. And then we got don't cares over here. Now here, we've only got 1, 1. We could use A or QA and not QB and not QC. So we could have that. But to me, it just seemed like it made it a little simpler to group all 4 of these and then have that DB is just QA. So I take the output from the first flip-flop and make it the input to the second one. That's fairly simple. Then for the third one, I've got 0, 0 for cell 0 and 1. Then I've got 1 in cell 2 and a don't care in 3. I've got a 0 and 4 and a don't care in 5, 6, and 7. So again, I've got a situation where I could just have 1, right, and have not QA and QB and not QC, or I can combine all of these and just say that the input to the third flip-flop is just going to be the output from the second one. So when I do that, I've got them all. So let's see what this is going to look like. I got to implement the design now. So here's my equations. That's all I've been working up to. I'm using D flip-flops. So here's what my circuit is going to look like. I'm using a positive edge clock. I could have used a negative edge clock. Doesn't really matter. Okay, this looks like that should have been slid over more. I don't know why I did it that way, but it's not going to be on the PDFs that you got, but that looks a little bit better here. So we've got the flip-flop. This is flip-flop A, and it's connected here, and A goes to input B, and B is connected there, goes to input C, and then I take A, B, and C and invert them and AND them all together and go to my input for A. I could have taken the Q naught outputs and just tied them all to AND gates, okay, and then used a clock. And then I could have had a negative going clock. Now, something you're finding out in the homework that you had to do, you have to have a reset or a set, don't you? You have to, because if this thing doesn't know what its current state is, it doesn't know what the next one's got to be. So we have to put clears in here, and at the very least, have the clears on the flip-flops, and I don't care if it's an active high or an active low, but let's say it's active high, so we have that clear signal go high for the first block in our systems and whatever the clock is, and then go low and stay low for the rest of the time we're running it. And that way it goes into 0 and then stays 0 after that. So here, I didn't use that. So here again, this is some older stuff. I've got model sim, and I started in state 0. Then I went to, on the next clock signal, which was a negative edge, I went to, or it must have been a positive edge that it chose. Went to 4, then it went to 2, that's a 2, and then it went to a 1, then it went back to 0, and then it went to 4, and then 2, and then 1, and then it went to 0. So everything worked just fine. I don't know if we have done too many of this type. Somebody in here, I know who it was, I'm just not going to use the name, was having some trouble with one of their circuits last night. And you can't just say that my Q outputs are going to equal not Q or be assigned not Q, because then you have to have Q on both sides of the equation. You can't do that. That's when Xilinx starts throwing errors at you. It doesn't do it all the time, but eventually, if you got everything else right, you get down to the point where if you got Q is assigned not Q, it's going to give you an error. You're not going to get to the end without it telling you you can't do that. So here you had to use a signal, and we let it be count. So the signal is a wire inside the entity that we can't get to. So I have a reset, and then that says put count, not Q's, but put count at 0. Okay. Else, so this is a synchronous type thing because it is based on no, it's not. It's just asynchronous because it says it's a 0. Else, if we get a clock event and the clock is 1, so we're going on a high transition, then if count is equal to 0, 0, 0, 0, then count goes to 4. All right. Else, if count was already at a 4, then count goes to 2. And if count was already at a 2, then it goes to 1. If it was already at a 1, it goes to 0. And we end our ifs. And then we come down here and let Q be assigned count. Okay? So here's where we're using the value or the variable count, the signal's count, but it's assigned to Q's, so that's going to be our 3-bit output of Q's, Q2, Q1, and Q0. So I put those in. I put this in. I ran it. That's why it was running on a positive edge. And when I did that on the positive transition, notice I had to have the reset. If I didn't have the reset, these would have been, I don't know, the whole time. It would have said, I don't know. So I would have got those orange lines across here. So here it's 4, then it's 2, then it's 1, then it's 0. Okay? And this is a great place to stop because I'm on the second example. And we will pick up from there on Thursday. Now remember, I can't hear hardly anything, but if you start calling me an asshole for all the fussing I was doing at the beginning, I'll hear that. And I'll be able to tell who it was that said it. I don't know why it's like that. I can also hear the car door slam when my granddaughter's coming to my house. Okay, that should be it for DE. See you later.